Imagine a fire that burns inside a house for, well, 20 years before anyone on the outside even smells the smoke.
Right.
No alarms trigger, no heat radiates through the walls, but by the time you finally see a flicker of flame in a window, the structural integrity of the entire foundation is already compromised.
Exact.
And for decades, I mean, that was the grim reality of an Alzheimer's diagnosis.
Yeah.
You wouldn't know the pathology was there until the cognitive decline became undeniable, and by then, the therapeutic window had largely slammed shut.
Yeah, and it was incredibly frustrating from a clinical perspective. We were essentially arriving at the scene of a biological fire decades too late. We were armed with nothing but medications that, might briefly clear the smoke, but they did absolutely nothing to extinguish the actual flames.
But to you listening right now, the paradigm has radically shifted. That 20-year silent window is no longer this impenetrable black box. Today's deep dive is centered on a sweeping, honestly monumental 2026 review published in the journal Cell by researchers from Washington University.
It really is a landmark paper.
It is. We are decoding the massive leaps made in Alzheimer's disease research over just the last 5 years. We're talking about mapping atomic-level molecular mechanisms, redefining the brain's immune response, and, the arrival of the very first disease-modifying therapies. Okay, let's unpack this.
The best way to approach this review is to see it as a blueprint for an entirely new era of neurology. We are transitioning from this historical focus on just palliative symptom management to a tangible future where Alzheimer's is not only treatable, but can be intercepted proactively.
Right.
But to understand how we intercept it, we really have to look closely at the exact physical biology of the enemies inside the brain.
Because we can't talk about dismantling a threat without understanding its exact physical shape.
Right.
And the traditional narrative always points to two main culprits, amyloid and tau.
Correct.
But the depth at which we now understand them is just staggering. So let's start with amyloid-β or A-beta. This doesn't just appear out of nowhere. It begins with the amyloid precursor protein, APP, which normally resides in the membrane of neurons.
Yeah, and under normal physiological conditions, APP plays a crucial role in neural growth and repair. But in the pathogenic pathway, APP is subjected to this sequential enzymatic cleavage. First, an enzyme called BCE1.
Which acts kind of like molecular scissors, right?
Exactly, functioning essentially as a pair of molecular scissors. So BCE1 cleaves the protein. Then a second enzyme, gamma secretase, makes another highly specific cut. It's this precise double cut that liberates the A-beta fragment, specifically A-beta 42, which is just highly prone to clumping together.
And the review highlights that this process is heavily regulated by genetics, right? Specifically, a neuronal receptor called SRR1. From my understanding of the sources, SRR1 acts as a sort of intracellular traffic cop.
That's a brilliant way to visualize it.
It directs the trafficking of APP, basically steering away from the cellular compartments where BAC1 and gamma secretase are just waiting to chop it up.
Yeah, and when you have a genetic loss-of-function mutation in SRL1, that routing system fails. The traffic cop is removed from the intersection. So APP is routed directly into the path of those cleaving enzymes, which radically accelerates A-beta production.
Wow.
And this accumulation is exactly what begins 2 decades before clinical symptoms even emerge.
Which brings us to one of the most mind-bending revelations in this review, and that's regarding cryogenic electron microscopy, or cryo-EM.
Oh, this changed everything.
Right. Because this technology lets researchers flash freeze molecules and map their structures down to the literal atomic level. For years, massive pharmaceutical companies spent billions developing drugs to target synthetic amyloid created in laboratories.
Billions of dollars, yeah.
But when they finally used cryo-EM to look at A-beta 42 filaments derived from actual human Alzheimer's brains, the structures didn't match. Wait, so does this mean a massive chunk of our legacy research was targeting an artifact that doesn't actually exist in the human disease?
Sadly, yes. It provides a very stark explanation for why so many promising late-stage clinical trials failed over the last 20 years. The differences were profound. Synthetically derived fibrils have entirely different side chain orientations.
So the shape is just completely wrong.
Completely. The way the individual peptides fold and stack to form the filament core is fundamentally distinct from the pathology we actually see in a human brain. You just cannot design a highly specific antibody for a target whose physical geometry you've misunderstood.
That is wild.
But, cryo-EM didn't just expose our past mistakes. It really illuminated a path forward. It revealed critical structural nuances between sporadic Alzheimer's, which is the common late-onset form, and dominantly inherited Alzheimer's, or DIAD, the aggressive genetic form.
And this is where that APNLF knock-in mouse model comes into play, right?
Yeah.
Because researchers finally found a genetic mouse model that produces A-beta-42 structures identical to the human DIAD filaments.
Exactly. Instead of just overexpressing human APP, which causes all sorts of artificial artifacts in the lab, they humanized the mouse's own AP gene and introduced specific mutations. We finally have an accurate biological testing ground.
Okay, so if amyloid's the match that starts the fire, the other primary culprit, tau, is the forest fire itself.
That's a perfect analogy. The dynamic between the two is really the engine of the disease. Normally, tau is a stabilizing protein. It binds to microtubules, which act as the internal scaffolding and transport tracts of a neuron. But in Alzheimer's, tau undergoes hyperphosphorylation,
Which means it gets chemically overloaded with phosphate groups. And because phosphate groups carry a strong negative charge, piling them onto tau drastically alters its electrostatic properties. It literally repels the microtubules it's supposed to hold together.
Precisely. That electrostatic repulsion forces the tau protein to detach from the microtubule. And without tau, the structural scaffolding of the neuron just collapses, severely disrupting cellular transport.
Wow.
Yeah, and then the detached tau proteins misfold and aggregate into those dense neurofibrillary tangles we always hear about.
Right, and the review goes so deep into the structural complexity of these tangles. It points out that it relies on alternative splicing of the MAPT gene, which creates different isoforms of tau, characterized by having either 3 or 4 microtubule binding repeats. They call them 3R and 4R isoforms. You can think of them as like different gauges of structural rebar.
And what's fascinating here is that different neurodegenerative diseases, which we collectively call tauopathies, feature different combinations of these isoforms.
Like progressive supranuclear palsy.
Right. PSP is primarily a 4R tauopathy. Pick's disease is primarily a 3R tauopathy, but cryo-EM revealed that Alzheimer's disease is unique. Its filament cores consistently feature this intricate, interwoven mix of both 3R and 4R isoforms.
So just to quickly recap for everyone listening, a beta starts the fire 20 years early by being cut by those molecular scissors. Cryo-EM proved our lab-made proteins were structurally wrong, and tau, the forest fire, spreads the destruction by collapsing the neuron's scaffolding.
That's the core of it, yes.
I mean, think about how you visualize diseases. Does knowing that these proteins have unique physical shapes change how you think about designing a drug to clear them? It totally changes it for me. We're talking about structural engineering at an atomic scale.
We really are.
But that brings us to the next massive question. Why do some people accumulate these tangled, misfolded proteins while others live into their 90s with completely clear brains?
Right, and that shifts our focus from protein architecture to systemic genetics, specifically the APOE gene. We've known for a long time that carrying the APOE4 variant is the strongest genetic risk factor for sporadic Alzheimer's.
Yeah.
But what this review beautifully articulates is how heavily APOE4's pathology is tied to the blood-brain barrier and to lipid metabolism.
Okay, there is a historical Easter egg in the sources that I absolutely loved here.
Yeah.
Back in 1906, when Alois Alzheimer was peering through his microscope at the very first described case of this disease, he documented seeing lipoid granules clustered near the plaques. He was looking right at fat deposits in the brain.
Yes.
Yet the scientific community largely ignored that specific observation for over a century, focusing almost exclusively on the protein plaques.
It's a classic example of confirmation bias in science. We saw the amyloids, so we ignored the lipids. Yeah. But APOE is fundamentally a lipid transport protein. It regulates cholesterol metabolism in the brain.
Let me pitch an analogy to you based on the mechanics of the paper. Think of the APOE protein as the brain's specialized cholesterol delivery truck. Neurons need these lipids for cellular repair and maintaining their membranes.
Right.
But if you inherit the APOE4 variant, you essentially have a fleet of structurally unstable delivery trucks. They don't bind to their receptors properly, and they prematurely drop their cargo. So you end up with a massive lipid spill accumulating improperly inside glial cells. And that toxic accumulation triggers a huge inflammatory cascade.
The delivery truck analogy holds up perfectly under molecular scrutiny. And this dysfunction isn't just happening deep within the brain tissue. It heavily impacts the cortical blood vessels, leading to cerebral amyloid angiopathy, or CAA.
Okay, what exactly is that?
Well, in APOE4 carriers, the beta doesn't just form plaques between neurons. It actually aggregates directly inside the walls of the blood vessels themselves.
Which degrades the structural integrity of the vessels, making the blood-brain barrier incredibly leaky. But here's the part of the paper that genuinely shocked me. We often treat the brain like this isolated fortress, right?
We do.
But researchers engineered a mouse model to express the APOE4 variant exclusively in the liver. The brain itself was producing normal APOE. Yet that liver-produced APOE4 was sufficient to massively exacerbate amyloid pathology and blood-brain barrier degradation in the brain.
Wait, really? The liver?
Yes, just the liver. It forces a total reevaluation of how we categorize neurological disease. Liver-derived APOE circulates in the peripheral blood plasma. It interacts with the endothelial cells, forming the blood-brain barrier from the outside in.
Wow.
This proves that Alzheimer's is not strictly a localized brain disease. It's a systemic, whole-body metabolic failure that acutely manifests in the central nervous system. So recap time again. APOE4 basically breaks down the blood-brain barrier. It causes fat to accumulate improperly because of those faulty delivery trucks. And liver-produced APOE4 affects brain health directly. I want you to think about that. How wild is it that a protein made in your liver can dictate the health of your brain's blood vessels? What stands out to you about that body-brain connection? Because to me, it completely shatters the traditional boundary we draw around neurology.
It really does. And, when those APOE4 delivery trucks crash and the vessels leak and the amyloid piles up, the brain's emergency response system goes into overdrive. Which brings us to the immunology of Alzheimer's, specifically the microglia.
Right, the microglia.
Microglia are the resident macrophages of the central nervous system. They're the innate immune cells. For a long time, their role in Alzheimer's was viewed somewhat simplistically. They're either the good guys trying to clear the garbage or the bad guys causing inflammation.
But it's more complicated than that.
Oh, definitely. The reality is a masterclass in biological nuance. The review centers heavily on a specific microglial surface receptor called TREM2.
TREM2, right?
When neurons undergo stress or damage, they alter their outer lipid membranes, flipping a molecule called phosphatidylserine to the exterior. This acts as an explicit eat me signal. TREM2 allows the microglia to recognize the signal and initiate phagocytosis, basically eating the bad stuff.
But the review describes them as forming a barrier, too. They don't just eat the debris. TREM2 allows microglia to migrate toward amyloid plaques, surround them, and physically compact them into ultra-dense cores. They are literally walling off the toxic edges of the amyloid plaques to shield the surrounding healthy synapses from damage.
Exactly. It's a fascinating physical defense mechanism.
Okay, but here's where it gets really interesting. If microglia are executing this highly protective compaction process via the TREM2 receptor, you'd think drug developers would be racing to create agonists that supercharge microglia. Why are we so hesitant to just turn the immune system up to maximum capacity?
Because of the collateral damage. This is the neuroimmunological double-edged sword. Yes, TREM2 activation is initially protective. However, microglia are highly reactive. Under the chronic, decades-long stress of unrelenting amyloid accumulation, they enter a disease-associated state.
Meaning they stop doing their job.
Worse, they stop effectively compacting the plaques and they begin aggressively secreting pro-inflammatory cytokines.
So they transition from being a localized protective shield to a biological blowtorch, essentially burning down the house to kill the spider.
That is exactly what happens. And the review points out that this sustained innate immune response eventually compromises the blood-brain barrier even further, and that invites the adaptive immune system into the brain.
Oh no, so like T cells.
Yes, we are talking about peripheral T cells and B cells infiltrating the central nervous system. Once the systemic immune system joins the fight, the neurodegeneration accelerates exponentially due to the crossfire.
Another quick recap for you listening. Microglia are your brain's emergency responders. TREM2 helps them compact plaques to protect neurons. But chronic inflammation eventually turns toxic. So if you were designing a therapy, would you try to turn the immune system up to clear the garbage, or turn it down to save the surrounding tissue? It's this incredibly delicate tightrope walk.
It is a massive challenge. You want to stimulate TREM2 enough to compact the plaques early on, but you have to suppress that secondary cytokine storm before it destroys the neural circuitry.
Right.
But of course, you can't balance that immune response if you don't even know the patient has the disease. Which pivots us to the diagnostic revolution outlined in the review. If clinical symptoms only manifest at the tail end of that 20-year silent window, how do we catch it earlier?
Historically, we couldn't, which is why clinical misdiagnosis rates hovered between 10 and 30%.
Right. Exactly. If a patient presented with dementia symptoms, doctors often assumed Alzheimer's, but autopsies would later reveal vascular dementia or Lewy body pathology. The shift from a symptom-based diagnostic criteria to a strict molecular biology-based framework is the most crucial logistical advancement in the field.
And the review dives deep into proteomics here. The large-scale analysis of proteins in the cerebrospinal fluid, the CSF. They mapped over 2,000 dysregulated proteins in the CSF of Alzheimer's patients. And one of the standout biomarkers identified is SMOC1.
Yes, SMOC1.
It's a matricellullar protein involved in early signaling cascades, and it is significantly elevated very early in the disease process, appearing in both the CSF and the blood plasma.
Finding molecular targets like SMOC1 allows us to track the pathophysiology in real time. But the absolute game changer, the advancement that will alter standard medical practice globally, is the development of highly specific plasma biomarkers for tau.
The p-tau blood test, the data on this is phenomenal. We're talking about assays that measure specific phosphorylated tau fragments, namely p-tau217 and p-tau181.
They are incredibly accurate.
The review shows that these simple blood draws correlate so tightly with the amyloid and tau burden in the brain that they are actively rivaling the accuracy of expensive PT scans and invasive lumbar punctures.
If we connect this to the bigger picture, we're looking at a near future where a primary care physician orders a p-tau217 panel right alongside your routine cholesterol check. We will be able to detect the molecular initiation of Alzheimer's disease decades before a patient ever experiences a single moment of forgetfulness.
That is just incredible.
It transitions the entire medical infrastructure from reactive crisis management to proactive intervention.
Quick recap on this section. Diagnosis is moving from symptom-based to biology-based. SMOC1 is a major new target, and p-tau blood tests are changing the game. Think about that for a second. Would you want to take a blood test that tells you your risk for Alzheimer's 20 years before symptoms start? How would that change your life today? Because proactive intervention is only useful if you actually have a weapon to intervene with.
Exactly.
And after thousands of failed clinical trials and decades of dashed hopes, this review formally welcomes us to the therapeutic era. We finally have FDA-approved, disease-modifying anti-amyloid immunotherapies.
It is a watershed moment. Lecanemab gained full approval in 2023, followed closely by donanemab in 2024. These are monoclonal antibodies specifically engineered to bind to different conformational states of A-beta and recruit the immune system to clear them out of the brain.
And the clinical data from the donanemab trials in particular is staggering. It proved so effective at clearing amyloid plaques that roughly 60% of the participants achieved complete amyloid clearance. They actually met the criteria to halt their intravenous infusions at 72 weeks. They stopped taking the drug because the target was entirely gone.
The success is undeniable. It significantly slowed the rate of clinical and cognitive decline. However, the review is very transparent about the mechanisms of risk, specifically ARI amyloid-related imaging abnormalities.
Right, we have to talk about the risks.
We do. We see two primary forms. ARIA-E, which is vasogenic edema, or fluid accumulation in the brain, and ARIA-H, which is microhemorrhaging.
So what does this all mean? Why does an antibody designed to safely clear a toxic protein suddenly cause brain swelling and bleeding? It circles back to the vascular damage, doesn't it?
It circles directly back to our earlier discussion on cerebral amyloid angiopathy. Remember that in many patients, especially APOE4 carriers, the amyloid isn't just floating between neurons, it's structurally embedded into the walls of the cortical blood vessels.
Oh, I see.
So when these highly potent antibodies enter the brain and aggressively strip that amyloid away, they leave the vessel walls temporarily weakened and porous. The blood-brain barrier is compromised, leading to fluid leakage and microhemorrhages.
Which highlights why careful genetic screening and MRI monitoring are absolutely mandatory for anyone receiving these infusions. But while donanemab and lecanemab are historic breakthroughs, clearing amyloid is really just step one. They slow the disease, but they don't halt the tau progression entirely.
No, they don't, and that's why the review looks to the horizon. And the future of therapeutics detailed here reads like absolute science fiction. We are moving toward genetic cellular engineering.
Right, like CAR T-cell therapy for cancer, but for the brain.
Precisely. We are talking about taking the principles of CAR T-cell therapy and applying them to neurodegeneration. Researchers are actively developing CAR-RM, which are chimeric antigen receptor macrophages, and CARA, engineered astrocytes.
Okay, walk us through exactly how this works in the brain. How do you engineer an astrocyte to fight Alzheimer's?
Well, you harvest the patient's own immune or support cells and genetically alter them in a lab. You program them with a synthetic receptor that possesses absolute hyperspecific affinity for a beta or misfolded tau.
Okay.
You then reintroduce these living engineered cells back into the patient. Unlike traditional antibodies that require constant, massive intravenous dosing to cross the blood-brain barrier, these engineered macrophages can cross the barrier naturally.
Oh.
Once inside, they act as an autonomous, self-replicating patrol force. They selectively hunt down and phagocytose the toxic plaques without triggering those massive, destructive cytokine storms associated with native microglial activation.
They are essentially designing intelligent biological nanobots out of the patient's own cellular material to autonomously clean the brain. It completely circumvents the need for repeat drug dosing. So, final recap. Donanemab and lecanemab successfully slow decline by clearing amyloid, but ARI is a serious bleeding and swelling risk. And genetically engineered CR astrocytes are the sci-fi future of treatment.
It's an incredible time for the field.
We are engineering the brain's own cells to eat plaques. Which therapeutic avenue gives you the most hope? When you look at the trajectory, from Alice Alzheimer's staring at undefined SAT deposits through a rudimentary microscope in 1906, to the deployment of pTau-217 blood tests, to the genetic engineering of autonomous CR macrophages, the velocity of this science is just breathtaking. We can finally see the enemy clearly, and we possess the actual tools to dismantle it.
The momentum is unprecedented. But, as this comprehensive review makes clear, we haven't quite reached the finish line. There is one profoundly important, unresolved biological mystery that the field is currently racing to solve. It's what researchers refer to as the tipping point.
The threshold between amyloid and tau.
Exactly. We know that amyloid accumulation happens first, and it acts as the catalyst, the match that starts the fire. We also know that tau hyperphosphorylation and tangling drive the actual neurodegeneration, the forest fire.
Right.
But what is the exact molecular trigger? What is the specific biological switch that gets flipped, causing tau pathology to detach from the amyloid cascade and become a semi-autonomous, self-perpetuating force of destruction?
Because the clinical trials show that once tau spreads past a certain neural anatomical threshold, even if you use donanemab to remove 100% of the amyloid from the brain, the cognitive decline continues. The fire has grown too large to care that the original match was blown out.
Precisely. Identifying that exact tipping point, whether it involves a specific threshold of microglial exhaustion, a particular inflammatory cytokine surge, or a secondary metabolic failure, is the ultimate frontier. If we can map that switch, we can deploy these therapies at the exact right moment to stop the fire before it reaches the forest.
It is a remarkable concept to consider. The idea that there is a definitive microscopic line in the sand inside the brain that dictates the entire cascade of this disease. I want you, listening, to think about the sheer scale of what we've explored today. Think back to that broken, murky diagnostic reality we talked about at the beginning of the hour. Alzheimer's used to be an invisible, unstoppable ghost. Today, because of cryo-EM, proteomics, and cellular engineering, that ghost has a highly defined physical shape, a known genetic origin, and a measurable footprint in our blood. The picture is sharper, clearer, and more actionable than at any point in human history. Keep diving deep.